I'll read it out loud. It says, "Hi, what I'm wondering most is if the discussion here will have differences with the lessons on linear regression in Codecademy." That is a good question. There will be some differences just in that this is more of an open discussion, and so if there's questions in the chat or there are specific things that anybody wants to talk about, we might go on some tangents and cover some things that are not in the lesson. But for the most part, we're going to start by going through the same content that's in the lesson. Yeah.
Cool.
Cool.
We are back in the office with our fancy streaming setup, so we're trying out like new mics, new cameras, all that kind of stuff. So let us know in the chat if anything is screwed up, if you can't hear us, if the mic sounds bad. But hopefully everything is working fine.
Yeah. All right. Shall we get started?
Let's do it.
All right. So the topic for today is going to be interaction terms and polynomial terms, which basically are ways that we can alter a simple linear regression model or a multiple linear regression model to make it a little bit more flexible and handle some different things that we might see in some data. So I actually think this is exactly the same to the question that was asked earlier. This is exactly the same data set that we give you in the lesson on Codecademy. And I believe it is simulated. I didn't write this lesson, but the idea behind this data is that we're imagining some sort of study that measures self-reported levels of happiness, self-reported or maybe like measured levels of stress, whether or not a person exercises. I think sleep is probably hours of sleep.
Makes sense.
Yes.
13.8 is a little
That's
extreme,
a lot,
but
maybe, and then maybe hours of free time per day. I think that's the intention of this data set. I'm pretty sure simulated though, so not real. Cool. So what we're going to get started with is visualizing some of this data. You'll notice actually in the lesson on Codecademy, and I just grabbed this code directly from there. You'll notice that we actually use this lmplot function to do a lot of the plotting in this lesson. The reason for that is partially because we haven't updated matplotlib and Seaborn in a little while. So this is an older function in Seaborn that does the same thing as the newer scatter plot function. But also it has the option to fit a regression line directly onto the plot if you wanted to. And so I'll just demo that really quickly. Here, actually, I'll demo it in a separate plot. So if I say, let's look at the relationship between stress and happiness. So is there a relationship between how stressed someone appears to be and how happy they report being? And I say fit reg equals true, and I think that's also the default. And I run this. I get, here are the points, and then it'll automatically draw this regression line for me, which is kind of cool, and it allows you to do this plotting a little bit more quickly, which is always fun. You'll notice that something interesting happens actually if I leave this as fit reg equals true and add hue equals exercise.
right, because now it's going to even be a little bit hard to visualize, right? Because there's three variables, right? There's stress, happiness, and exercise.
Yeah. It's pretty smart actually. It will do something here. It'll actually draw me two regression lines, one for exercise equals 1 and the other for exercise equals 0. Alex, do you notice anything weird about this plot though that's like different from what we might expect based on everything we've covered so far? Like, do you remember I think maybe it was the last stream you joined me on, where we started talking about using a categorical variable in our regression, and we plotted some regression lines when we included a categorical variable in the regression.
Right.
And the two lines had something different from what we're seeing here. Do you remember?
No, I don't recall.
Okay. So so actually the two lines were parallel. So there was no way previously, or we didn't have a way previously to draw regression lines that were like totally just fitting the orange points and the blue points separately. We could only change the intercept. So if you go back, you watch the older video, you'll see that in action. And today we're going to actually learn how to fit these lines so that they can have different slopes.
Yeah. And in that graph, are these lines, so say you took out all of the blue circles and just fit it to the orange x's, is that the orange line? And similar to the other way around. So they're completely independent of each other. They're basically ignoring the other set of points. Okay.
Yes. If you fit just a regression for the orange line or orange points and just a regression for the blue points, you'd get these lines.
Okay, cool.
So I'm gonna now just show you this plot without the lines. I think I kind of gave away the end goal before we even got started. So we'll start back at the beginning, and we'll motivate this by saying sometimes when we look at a plot of two quantitative variables and then we color by categorical variable, we'll see that if we were to draw a line through just the blue points and if we were to draw a separate line through just the orange points, those lines would probably have different slopes and different intercepts. Whereas up to this point, if we just added, so if we just fit a model where we did like happiness as a function of stress and exercise, we'd end up with a model that allows us to draw separate lines for these two sets of points, but they would have to have the same slope. They could just have different intercepts. And I'll show you on the iPad in just a second mathematically why that happened, and then I'll show you how we can now fit a regression that visually would look like this.
Cool.
So what I'm going to do is let's add a chunk and let's fit this regression right off the bat. I'm going to grab this code from over here and we're going to talk through it for a second, and then we'll come back to this in a minute. Okay, so I'm fitting this model. I believe I've already loaded, yes. So I'm fitting this model, and it's happiness as a function of stress plus exercise plus stress colon exercise. Now, for a second, let me remove this. This is what we've done so far in previous live streams. So if I run this is kind of what we've seen before. We get an intercept, we get a slope for stress, and we get a slope for exercise.
So same intercept. So these lines aren't parallel. It's same intercept and different slopes.
So these lines actually are parallel. So actually, this is a good place to kind of like come back to this. I hadn't initially planned on it, but I think this is like a good reminder. So let me actually.
Can I flip you over?
You can flip me over, but can we leave that up? Yes. Okay, great. So this is for the other one that had the stress colon exercise, but I'm just going to write down the values for the other regression for a second. So for this one, we had an intercept of 10 about. We had a slope on stress that was equal to negative 0.7. And then we had a slope on exercise that was equal to about negative 0.9. And we fit this model, it was happy as a function of stress plus exercise. And what that meant was that we were fitting this model. We fit something that looked like happy equals intercept, which we called B0, but we'll replace that, plus B1 times stress plus B2 times exercise. I'm just gonna abbreviate. And so plugging in B0, B1, and B2, we got something like happy equals 10 plus, well, it's really a
Negative.
plus negative, so minus 0.7 times stress minus 0.9 times exercise. But remember that there are only two possible values of exercise. Someone can exercise or not exercise.
Got it.
So we ended up with two separate equations. One, when exercise equals 0, we get happy equals 10 minus 0.7 times stress minus 0.9 times 0, but 0.9 times 0 is 0, so that kind of goes away. And then the other one we got, I'll write it down here, when exercise equals 1, we get happy equals 10 minus 0.7 times stress minus 0.9 times 1, which is just 0.9. And so then we end up with happy equals, we can take the 10 and subtract the 0.9, right? Because order of operations, we can, all of these addition and subtraction things can happen in any order. So we end up with like 9.1 minus 0.7 times stress.
Got it. So same slope, different intercepts.
And so they both have the same slope on stress, but the intercept is 10 when exercise equals 0, and the intercept is 9.1 when exercise equals 1. And so that slope on exercise is really the difference in intercepts for the two lines that we would draw. Oh, I'm now realizing that that we are covering the
It's there.
oh well.
You're gonna scroll down on the
I
iPad.
can't. Darn it.
Well,
Sorry guys.
yeah.
Oh,
Yeah.
Alex
I
is
don't
gonna
even know. It's there.
All right.
We're figuring out the green screen.
Sorry, guys. Hopefully that was clear, though. Okay, so now let's go back to that second. Can we switch back to the?
Yeah, that's just okay.
Yes. Okay, so that was when we just fit this, where we had happy as a function of stress plus exercise. But now we're going to add an interaction term, and the way we can do this in stats models is we can just say, I want an interaction between stress and exercise by putting a colon between them. So now when we run this model, now we get an intercept, we get a slope on stress, and then we also get a slope on exercise, just as before, but we get now a third slope on stress colon exercise. So now we're going to take this and we'll go back to the iPad in just a second and talk through what those, sorry, I'm erasing really quickly, talk through what those translate to in terms of our model. Okay, so now, well, that's okay. So now we see, okay, we had intercept, stress, exercise, stress, colon, exercise. All an interaction term is an extra, it's almost like having an extra column in your data that is the product of two other columns. So it's almost like an extra feature that is just the product of two others. So the way this looks like in terms of the model is we're fitting now happy screwed up. Let's see. So now we're fitting happy equals B0 plus B1 times stress plus B2 times exercise plus B3 times stress times exercise. Times sign.
Okay.
Okay. So in like for example in Sklearn, you have to create an interaction term yourself in your data frame, and literally what you would do, and we can demonstrate this after, is you would just multiply everything in the stress column by everything in the exercise column and create a new column of your data frame called stress exercise. And then you would just add that into your model as a predictor.
I think I'm a little bit confused of like what the overall goal is here, because so in this situation, isn't this going to still result in two parallel lines, because that times 1 times 0 is still going to be I can't even that's not pointing at anything. It's still going to be right when exercise is equal to 0, the B2 times exercise and B3 times stress times exercise, all of that is just going to go to 0. So isn't this really similar to the last thing that we just looked at?
It's very similar, but let's actually walk through exactly that. So let me plug in all of these numbers. So we've got happy equals, our B0 is 12, that's still our intercept. Then we've got B1, it's negative, so we're going to do B1 is negative 0.97, so minus 0.97 times stress. And then again with the negative sign, minus 3.1 times exercise, and then we've got plus 0.36 times stress times exercise. Okay, now let's break this up into two separate equations. I like this eraser never works the way I want it to. Okay, so let's break it up into two separate ones. One where exercise equals 0 and one where exercise equals 1. So I think you, Alex, were doing the exercise equals 0, 1 in your head first. So it's a little simpler. So let's do that first. So when exercise equals 0, we've got happy equals 12 minus 0.97 times stress. And then we've got minus 3.1 times 0 plus 0.36 times stress times 0. Now, like you were saying, right, anything times 0 is 0. So 3.1 times 0 is 0. But also 0.36 times stress times 0. Even though we're multiplying stress in there, it's still like a bunch of things multiplied by 0. So that's also 0. Mm-hmm. Okay, so that's 0, that's 0. So our equation is really just happy equals 12 minus 0.97 times stress. Okay, so we've got our line again for exercise equals 0. Now let's try exercise equals 1. This is where it gets a little bit more complicated.
Yeah.
So we've got, and also if anybody has questions as we go, I know this is like, again, a little bit of math. So ask us questions if they come up. But for exercise equals 1, we've got happy equals 12 minus 0.97 times stress, just like before. Then we've got minus 3.1 times 1. And then we've got plus 0.36 times stress times 1.
Got it.
Okay, so multiplying by 1 doesn't change the value of anything, right? So we can do the same thing as before with our intercept, right? So like this minus 3.1 times 1, we can just add to the 12. Again, order of operations. Since this is just like multiplication and addition, we can add or subtract these terms in any order, so we can combine these two together. So I'm going to do that first, and then I'll write out the other set. But some of you might already kind of see what that's going to be. So we've got happy equals, and then 12 minus 3.1 is like 8.9.
Yeah.
Right. And then we've got minus 0.97 times stress. And then we also have plus 0.36 times stress. And then I'm going to just drop the 1 because anything times 1 is just equal to itself. And now we've got minus 0.97 times stress plus 0.36 times stress. And so both of these things are multiplying stress. So we can actually factor stress out of this like piece right here. So stress is multiplying both things. We can factor it out and add the minus 0.97 and 0.36 together. And so what we get is something that looks like this. We get happy equals 8.9. And then we've got, I guess I'll put like plus stress times, and then we've got the minus 0.97 plus 0.36. Oops, 0.36. And that, again, like thinking about how you would calculate this or like how you would expand this, right? You would multiply stress by both things inside the parentheses. So you'd get back to what you had above. You'd have the stress times minus 0.97. That's this term from before. And then you'd get the stress times 0.36, which is this term. So we just factored it out, but we rewrote that same thing as before. And then minus 0.97 plus 0.36.
61?
Yeah. So we got happy equals 8.9 plus 0.61, or sorry, minus 0.61. I guess I shouldn't have switched the order, but you can multiply in either order. So, okay, so that's our equation for exercise equals 1. That's our equation for exercise equals 0. And you'll see that they have different intercepts, 8.9 versus 12, and they have different slopes, minus 0.61 versus minus 0.97.
Cool. And so, right, the change in slope came from this term that included both stress and exercise. That was the thing that ultimately affected the slope when exercise was 1.
Exactly.
Could you briefly describe again how the 0.36 was calculated from the original data? Right, so these numbers that are up in the top left corner, where did those even come from?
Oh, so these numbers came from fitting the model. So we'll go back to the Jupyter notebook in a second. But basically, when we fit the model with that interaction term, it calculated a slope on the interaction between stress and exercise. And that is basically like a multiplier, right, of stress times exercise. So then we just followed that out in the model. I also see a really good question in here about, it says, would we consider the third variable, stress times exercise, dependent on the values of stress and exercise, that you get more accurate models when all your feature variables were independent? So that's a really good question. I'm not sure how great of an answer I can give, but all to say, so yes, you you don't want to have or you don't want to have highly correlated variables in a model together, because if they're both explaining your outcome variable, then the model is going to have some trouble estimating the coefficients for both of them, because they both have the same explanatory power in terms of your outcome variable. And it also, right, if they're highly dependent, like if you just take if you take one of the columns and multiply it by a number, theoretically you shouldn't be able to fit that model at all, because your new variable is perfectly correlated with your old variable.
Right.
In this case, it's not perfect. It's not like this new variable that we created by multiplying stress and exercise. It's not perfectly correlated with either stress or exercise, because we're multiplying by a different value for each. So like if you think just about stress, whether you multiply it by 0 or multiply it by 1 depends on the value of exercise. So there's no way you could just take that column without seeing the exercise column and get the new one.
Right. It's not like if you were just doubling stress, that would be perfectly correlated with stress, but there's, it's either you're sometimes multiplying it and sometimes not, depending on if exercise is 0 or 1.
Yeah. But on the flip side, there are reasons why you might not want to just create like the most complicated model that you can with as many extra predictors as you possibly could create. Because you could imagine, like, if you have, 10 columns of a data set, which is, even in real life, that's like pretty small. You could imagine you could create an interaction term for every possible pair of variables, basically, pair of features, and that would be a very large number that I don't know what it is off the top of my head, but yeah, but that'd be a very large number, and you could create a very complicated model to model like every possible interaction. But that's not always a good idea, because what ends up happening is you end up overfitting, and that's kind of actually a very important topic in a newer course that we're building right now on feature engineering and like regularization. But basically, if you fit your data too well, then your model is not going to be very good at predicting outcomes for new data. So like this model, if I make it super complicated, might perfectly fit my data that I collected on my like 100 patients or whatever. But if I go out and I find another patient, like this might not be a good way of explaining the relationship between these things.
Right, because you were like so dependent on those original 100 patients.
Exactly. Cool.
Can you describe just like the total takeaway or upshot of this whole process? Because what I'm walking away from this is, before we were able to draw two lines that were parallel, that kind of stinks for some reason, and now we can draw two lines that aren't parallel. Like, what is like the thing that I should be taking away from creating this this new variable?
Will you go back to the picture or the
browser?
The browser. Yeah, so that's a really good question. I think so. A couple of things. First of all, it just, if you were to plot your data and you see this picture, maybe you see something even more obvious. Like maybe you see these lines look completely different. Like maybe you even see that for people who do exercise, the relationship between happiness and stress is this like negative relationship. Like people who are less happy are more stressed. But for people who don't exercise, maybe it's like a positive relationship. And so what you actually see sometimes, and this is sometimes I think referred to as Simpson's paradox, and we actually have, here I can go in and show you in the lesson.
As a note, so we're using new streaming software, and your mouse pointer isn't showing up on the software. So if you're ever gesticulating with the mouse, that's not getting picked up.
That's good to know.
Something we can play around with.
Is it? Oh, it might not be in this lesson. Which lesson is it in? Let me see if I can find it quickly. I think it's in this lesson. Yes. So this is like a more complicated example here. Let me like pull this up. But you'll see, right, like in this example, we've got like a positive, if we were to just like ignore this categorical variable and draw a line through all the points, we would draw this black line, which is like this positive relationship. But then if you add this this like categorical variable to the model, and you're trying to draw the lines now based off of you're basically trying to draw the lines through each set of points. In this example, they're parallel, so like we're not constricting, but you'll see, right, that like the lines have negative slopes, even though the initial relationship between these two variables in among all the points is positive. If you zoom in, you now are getting these like negative relationships. And so you can see stuff like that where like maybe one of these relationships is negative and the other one is positive. And if you didn't fit anything, like you didn't fit any sort of exercise term, like you'd end up with a flat line. You'd think there's like no relationship between happiness and stress. But like once you add this to the model, you suddenly start seeing them. But now if you are restricting this so that those lines have to be parallel, then you're like ending up with, you're going to end up with maybe like two parallel lines that are flat. And that's like not going to model your data super well. So there's definitely situations where adding an interaction term means that you significantly improve your model from where like you basically can't explain anything to oh, it looks like we didn't switch over maybe.
That's paused.
Oh, sorry.
Yeah, you're good.
Okay. But yeah, so sometimes it significantly improves your model. Okay. I think like the flip side, or the other thing that maybe is like the other half of the answer to that question is, and maybe this gets a little bit more into like when we do this, is we do this when we think that the relationship between the outcome variable and one of our features is moderated by or like influenced by some other factor. So in this example, it looks like, right, the relationship between stress and happiness is maybe like less steep. Here, I'll do it with the lines. Is less steep for people who do exercise. So like maybe people who are exercising are more like immune to stress in general, and so like being more stressed has less of an effect on their happiness than among people who don't exercise. It's a steeper line. And so we're saying that like we think that, you know, more stress has like more of a effect, I say in quotes, because like we're not really, depending on how the studies run, we don't know if this is like a causal relationship, but the effect of stress on happiness is more significant among people who don't exercise. And so we think like there's some exercise is moderating this relationship, and that's why we might think like we want to be able to model that in some way.
This is maybe a tricky question, or this is maybe a tricky question, but like how do you do this in the real world of like, so you just described, oh, we have this situation where one set of data points has like a negative slope, one has like a huge positive slope. We want to be able to draw these two lines with different slopes in order to capture that, and so we want to do something like this. But do you know that by plotting the data and looking at it? Do you like just give both things a shot and like see what the models look like after trying to add it or trying not to add it? Like how do you actually do this with a data set that you don't know anything about?
That is a great question. So you can certainly, and I highly recommend, in fact, I'm working right now on some content on exploratory data analysis, and it's definitely a good idea to, before you fit a model, take a look at some of these relationships and try to see whether maybe you have hypotheses, like maybe you know something, you have some prior research about the relationship between all of these features, and you have some hypotheses about what might be moderating what relationships, and then maybe you get some data and you want to take a look at it before you try to fit the model. And so that's one thing you would do. The other thing you can do, which is more like post hoc, is you can compare different models. So you could fit it both ways, and then you could see, like the simplest thing is you might calculate like a mean squared error, like basically, or a total squared error, whatever. Basically, like how far off are all these points from their respective lines, and you could calculate that for both models, the one where you don't include the interaction and the one where you do, and then you could say like, okay, I see that when I add this term to the model, it significantly improves its ability to explain this data. And you'll actually see, if you're following along in this linear regression course, there is a section here on choosing a linear regression model that starts to cover some of those methods that you could use to compare two different models once you fit them, to get a sense for whether both of them make sense, or whether one makes sense over the other. Then there's also additional things you can do, like regularization, which Nitya is working on right now, that can even further like help you basically like fit the model at the same time as estimating whether like those parameters are useful. So cool. That was a bit of a tangent, but hopefully. I see a question. How do you do feature selection in linear regression? I've heard of forward and backward elimination methods, but don't know what they do. Again, this is like a plug for all the content that Nitya is currently working on. And that will be, I think, going live at the end of the summer, early fall. But essentially, so forward and backward elimination are essentially methods for like sequentially adding terms to your model. So like maybe you want to sequentially add different interaction terms and reevaluate the model every time. And then if adding the term improves the model, you keep it. If adding it doesn't improve the model, then you don't keep it and you try something else. Or you start with like all of them in the model and you sequentially like delete things that are not helping you. That would be backward elimination. And then regularization is essentially a way that you can fit this model with like an extra term so that you allow some of the coefficients to get really small or even go to zero. And that's kind of a way of like, I don't know, eliminating those from your regression. Okay. And then suppose I have data. Can I add 2 extra decimals on 0.56? Oh, you can add as many decimals as you want to run the linear regression. Yeah, as much, I mean.
I don't know if that's that.
Is that not the question?
Yeah, the question is saying like, oh, if I have this data, can I add, or the way that I'm interpreting this question is, can I add points between my existing points in like regular steps of like, can I add 0.5611, 0.5622, 0.5633, like can I add data that falls along that line? I think that that's what the question is asking, but if you want to clarify the question.
So I guess like basically I think you can't add data if you're trying to answer a question about some data or like fit a model to some data, then you probably don't want to alter your data before you fit the model. But yeah, I mean, if it's like something that you could collect, so like if these are values of stress and you don't have anyone in your data set who reported like a value of 0.5611 for stress, but you can go out and find someone and you can record their happiness score, then you could add that to the model. If you don't or you could add that to your data to fit the model. If you can't find someone with that value, you shouldn't just like add that to your data set before you fit the model.
Got it. And the clarification in that question of if 0.56 is occurring multiple times, can I add extra decimals to it?
So I still don't fully understand, but yeah, if you see multiple people with this value of 0.56 and you are able to measure more specific values, then yeah, like if you are able to measure to the 4th decimal place, but most like measurement tools have some limits. I also see a question about heteroscedasticity, which is a fun word. I think that is coming in the next live stream.
What a plug.
What a plug, yeah. So yeah, we'll come back to that next week. Cool. So I think we got like 20 minutes left. I want to cover 2 more things if we can fit them in. So one thing I'll kind of go over a little bit more quickly, but I will pull this over and rerun in our other notebook. So I just want to demonstrate. So up to this point, we have shown that we can fit this interaction term with a categorical variable as one of the terms that we're interacting. So in that case, we ended up with just 2 lines because there are only 2 values of exercise. So you basically get like a separate line for each value of exercise. But we can also fit interaction terms with 2 quantitative variables. So here's another plot. It shows the relationship between happy and stress. And then we've colored by this value or this other variable free time, which is like the number of hours of free time that you have. And this is also a quantitative variable. We're just showing values, like integer values for the key, but you could imagine this is like a scale where people that have more free time are darker colored dots and people that have less free time are lighter colored dots in this plot. And you could imagine, like, I can't do this super easily in my head, but you can imagine if you just isolated all the people with 5 hours of free time, you might draw, oh, I am remembering now that you can't see my pointer, but right. So if you just isolated all the people, all this, like the darkest purple dots, the line that you draw through those might be different from the line that you draw through the lightest color dots, the people with 0 hours of free time. And so, so we can fit this for this setup as well. So I'm going to go ahead and grab this model again, and we'll edit it a little bit. So this time, let's edit this. Let's do stress plus free time plus stress interacted with free time. And then let's fit that. And we can fit something again. We see we get our intercept, slope on stress, slope on free time, and also a slope on free time colon stress or stress colon free time. And I'll just write this out super quick on our iPad again. Okay, cool. So here we've got those written out for ourselves, and let's write out what this model is super fast. So the model is exactly the same as what we had before. We've got like happy, we've got happy equals B0, which is 8, plus, and again with the minuses, sorry, minus 0.55 times stress, plus 0.12 times free time, and then plus 0.04 times stress times free time. I'll abbreviate FT. Okay. And then you can see for different values of free time, we get different equations. So for example, when free time equals 0, our equation is just like happy equals 8 minus 0.55 times stress. And these two other terms go to 0 because 0.12 times 0 is 0, and 0.04 times stress times 0 is still 0. And then when free time equals 1, we get happy equals 8 minus 0.55 times stress, and then plus 0.12 times 1, which is just 0.12, and then plus 0.04 times stress times 1, which is just 0.04 times stress. And so if we simplify this, oops, I don't know how to go back. Standard. Did that change? Yeah, you can see it. Oh well. Oh no.
This back button. Oh, yeah, it works.
I'm just gonna like reopen it. Cool. So we've got happy equals 0.8. And then we've got the minus 0.55 plus 0.04. So it's going to be like minus 0.51 times stress. And sorry, I should have added, it's 0.8 plus 0.12. So this is going to be like 0.92 over here. So it's going to be 0.92 minus 0.51 times stress. And then we can keep doing this for other values of free time. So we can even do for free time equals 2. We're basically going to end up adding another 0.12 to this intercept, because we're going to end up with, right, 0.12 times 2 instead of 0.12 times 1 in this equation. So for free time equals 2, our equation is going to be happy equals 0.92 plus another 0.12, which is going to be 1.04. And then we're going to also add another 0.04 onto the slope. So it's going to be like minus 0.47, right? Times stress. And so we can do this for every value of free time. We get a new equation. Every new equation has its own intercept and its own, its own intercept and its own slope. And we can try to visualize it. It's a little bit harder to visualize because now we have, I only did integer values of this, but like you could imagine there's a different line for every possible value of free time. So you could also have like free time equals 1.5. Theoretically, you could also have free time equals negative something. But obviously that's not realistic. But here, sorry, I can't see.
Sorry, yeah.
I'm gonna have you switch us back. Okay, so we've got like infinitely many lines in here, but we can visualize what some of them would look like. I think I grabbed this, and I will really quickly talk through what this code is doing. I think in my initial, I called this model Q. Okay, so here's 3 lines. Those are the 3 lines for for free time equals, I think, 0, 3, and 6.
Got it.
And so you can see what I'm doing is I'm modeling. So for each line, I'm taking the stress values, and then I'm taking the intercept plus the coefficient on stress. That's all I need for the first line when free time equals 0, because remember those other 2 terms kind of go away. but then for my line when free time equals 3, I'm basically like writing out this whole equation. It's like, this is my B0, this is my B1 times the stress values, and then this is my B2 times 3 times, this is my B2 times 3, which is the value of free time, and then this is my B3 times stress times 3. So I'm basically plugging in a value of 3 for free time into that equation in order to draw this line. And so that's like the second line, and then the third line for free time equals 6 is this dark purple line, and you see that they all have different intercepts and they all have different slopes. Cool. Okay, so that's it that we're going to cover for interaction terms for right now. Were there any questions that you wanted to cover?
Yeah, I've been chatting with people in the chat, so if you've seen me typing, that's what I was doing. Let's see. There was one. Where did it go? What are the AIC and BIC criteria?
Cool. Yeah. So those we're going to cover, I think, 2 live streams from now. And like I said, that's all in this course menu. That's in the choosing a linear regression model lesson. You'll find lots of stuff about AIC and BIC. Here we go. Here's an exercise on it. So those will come up later. I also see a question about fixed effect and random effect models. That is something, so what we're doing right now is fitting fixed effect models. Random effects are useful for different kinds of problems. Like, I think the classic one is when you have data where the observations are not independent. So like students within a school are not independent. And so if like you have school as a predictor in your model, and also like individual students within each school, you want to account for those, like that collinearity or that correlation. I don't think we currently have any content that covers that, but yeah, like a random effect is basically like it's like an extra term in your model that is basically like random error. That's like but the random errors are correlated within, like, say, a school or something.
Lots of questions about office hours. Do you want to plug what we're doing there?
Oh yeah, so office hours, we did our first test run last week, and then we'll have another office hours this week. We're doing them on Discord, and it's basically just a place where you can come and ask questions, and we have voice capabilities, so we can like answer them speaking. We can also share our screen and show you stuff if we need. And but it's also, we also have a like a chat on Discord.
Oh, yeah.
Where you can post questions at any point, and if you post your questions ahead of time, I think it's called Questions Bank Curriculum now. But we'll be checking that and keeping an eye on it. We're not going to respond like right away probably, but if you have questions, we'll look there before office hours so that we can make sure we get to anything that is asked ahead of time. Cool. Okay.
Yeah, we also have, someone was saying in chat if we could do office hours directly after this stream. That's something we weren't planning for this week, but if folks would prefer that, if you're here anyways watching the stream and want like more time to chat and ask questions right away, we could potentially make that happen.
Yeah, for sure.
So
yeah, that's good feedback.
Similarly, it sounds like there's a cool Python package that will let us like render math equations quickly. So yeah, more awesome. Feedback. If like, I like what Sophie is doing with the iPad. I think it's helpful to be able to like draw graphs and stuff. But if there are ideas that you have that would make this better, yeah, definitely let us know.
Cool. All right, I've got one more thing that I can show you guys since we have time. So lastly, another kind of flexible model that we can create is using polynomial terms. So I'll show this graph right here. Again, a little bit made up, but this is sleep versus happiness. And so we see, I guess the, we'll do LM plot.
Yeah.
Oh, it's, oops. Hold on, I got this. We got sleep, happy, and then what was the data called? Happiness. All right, let's try that. Okay, so it's gonna fit this line if we just leave it as fit reg equals true. But you'll notice, actually, I'll add the like fit reg equals false. Rerun, right? You notice that if you were to try to like draw a line through these points, you would say, okay, like as you get more sleep, your happiness increases up to a point. If you get more than 10 hours of sleep, your happiness is starting to like decrease again. And so we almost want to be able to fit like a curve to this instead of a straight line. And with regular linear regression, we don't have a way to do that. So we can do it using polynomial terms. And this is, again, a little bit of like a trick of almost adding another term into our model or another like column into our data that's based off of another column that already exists. And it basically allows us to have a model where we have like a squared term in the model, or so like a higher order polynomial. So I'm going to demonstrate this really quickly with this data. And we want happy as a function of sleep this time. And then we're going to add I think it's like this. Basically, this is taking sleep to the second power. Let me just make sure that that's, oh yeah, that's right. Okay. So we're just saying, okay, I want to add sleep squared into my model and then fit this and then print this out. Let me get model P for polynomial. And then, whoop, oh.
Model P dot terms, yeah.
Yeah. And then you'll see that we get a intercept, we get a slope on sleep, and then we get a slope on sleep squared. And I'm not going to switch to the iPad now because we're kind of running out of time, but I'll actually do this like mathematically. I'll write it out in Python. So basically what this is doing is it's creating a new equation where we have sleep squared in our model. So let's like, I guess, save these as B0, B1, and B2. So model.params 0. So like the first thing is the intercept. That's our B0. B1 is the second thing in this model. So that's at index 1. And then B2 is at index 2. So I'm just saving these numbers as B0, B1, and B2. I'm gonna also just save the values of sleep as sleep instead of like happiness dot sleep because it's a column in my happiness data set. I'm gonna just save it separately as sleep. And then I'm gonna say like predicted happiness based on this model is now equal to B0 plus B1 times sleep plus B2 times sleep squared. So I can do that as like sleep star star 2, that will square all the values in sleep. I could also do like numpy dot power sleep comma 2. But basically, right, this is like all the values in this column squared. And if I plot this now,
and the result there is going to be a column, right? Because sleep is a full column, so you're doing that for every value in this sleep column. You're doing that equation.
Exactly. In fact, I can also just show like what this looks like. So I'm gonna run this so I have them saved, and then yeah, basically like this is every value in sleep squared and then multiplied by B2. I guess we can just do that. This is every value in the sleep column squared. So, okay, so I'm just creating these predicted happiness scores. And then what I can do is I can add it to this picture so we can see what it looks like. And I'm going to plot sleep and predicted happiness based off of this model, and I'll show it. Whoop. I guess actually, what is a better way to do this? I guess now I'm realizing this is not pretty because it's like drawing the line between all the points. When we're doing it on a line, all of these were like still on top of the line. So let's see, we can just do like lin space, or we can do like sleep equals, so sleep is roughly between 0 and 14. So let's, instead of grabbing this actual column, we can do like, is it in NumPy?
So you just want like a list of values from 0 to 14 or 2 to 14?
Yeah. By 0.5 or 0.1. Here, let's just test this really fast. And then no.
Let me look it up.
Thank you. Here, actually, I can demo this, even though we're lin space, and then start, stop, and then
Num equals
50. Oh, so then it's just like the third parameter is the number of values. So we'll do like 100 values, and that should give me, yeah, okay. Sorry guys, but hopefully this is helping you see like how we do this in real life.
Yeah. And so here we're not using the actual sleep data. We're making up a bunch of fake points just to draw what this line looks like.
Right. And then, yeah. So that's a little nicer. Now we see that that polynomial term allowed us to create this like kind of curve in our line.
Cool. Quick question was, so when we did sleep times exercise, that was the interaction term, and if we're doing this sleep squared, is that called the polynomial term?
It is a polynomial term.
Cool.
Yes. And we could even add sleep cubed and sleep to the fourth. We could add more and more polynomial terms, but again, like we probably don't want to. If we added like a cube term, that would allow us to get like another curve in the data or in the line basically. But then I think there's some really good examples of this. If you just like add lots and lots of polynomial terms, you could have like a very squiggly line, which is a good example of overfitting in action. Cool.
Cool. Sophie, you're going to be gone for office hours this week.
Yeah, I might sign on though.
Okay.
We'll see if I can. I might be gone for office hours though, but I'll be back next week and I'll keep an eye on Discord.
Yeah, I'll be in the office hours. I am not the stats person that Sophie is, so I don't know if I'll be able to answer your stats questions, but
I could probably get Nitya or
yeah,
Andrea.
we'll find someone
Yeah.
that knows what they're talking about.
Andrea actually wrote all this lesson, so
Okay.
maybe I can get her to do it.
Cool.
All right, cool. Well, awesome. I'm glad that our first
Stream back
like
in the
real
office.
stream
Yeah.
worked. I love this green screen and the fact that we're just like
Yeah.
hanging
I don't know
out.
if you noticed, but I shrunk us in the middle of the stream to.
Oh, that's good.
yeah.
I like it.
Um,
It's like tiny people in the corner of the screen. Awesome. Well,
Cool.
thank you everyone for coming. And if you have questions, ask us on Discord or ask in the comments on the YouTube video.